Good evening and welcome to Gibson's Bookstore Remote. I am Elizabeth, the events coordinator for Gibson's Bookstore, and I am joined this evening by author Chad Orzel. Hello, Chad.
Hello.
Chad is the author of A Brief History of Timekeeping, the Science of Marking Time from Stonehenge to Atomic Clocks. This is really cool. I really love books on like the minutia of like a small piece of history, and you're just like, I never really thought about the iterations of clocks, but here we go. And then you really just dive into it, and it's really cool, and all the greater implications for society that you never really thought of. So this book is available from Gibson's Bookstore. To our audience members, if you have questions that you would like to ask towards the end of the event or for us to incorporate into our conversation, please do put them into the chat sidebar or into the Q&A box. We will get to them, or just cool comments or clock stories, where I'm seeing a lot of clock stories in the chat sidebar, and it's very interesting. Chad, please tell me a little bit about A Brief History of Timekeeping.
Sure. So I'm going to do the screen share thing and give you some images that I've got here. And let's, is that the right one? I think that's, yes. So this is the cover of the book, and uses as a visual the thing that most people probably think of when you think about time and timekeeping, which is these gears from inside a clock, right? So bits of clockwork and intricate machinery, and that's probably what you think of if you think about the history of timekeeping. And you probably think about mechanical devices that are relatively recent inventions. But one of the things that I'm trying to do with the book is to argue that the history of timekeeping is in fact much deeper than people necessarily realize. And this goes back to very ancient times, before sort of recorded history. And sort of the oldest kinds of timekeeping that there are fundamentally based on the sun. And these are a couple of examples here. In the upper left, you've got a sundial, and then the lower right is the New Grange Monument in Ireland. I'll talk more about that in a minute. But both of these work based on the motion of the sun, and this sort of illustrates the key central idea of timekeeping, which is that a clock is a thing that ticks. Now, not necessarily an audible tick like a grandfather clock, but it's something that does some regular repeated action that you can count the repetitions of and use that to mark time. Now, in the case of a sundial, right, the regular repeated action is just the course of a day, right? The sun rises in the east, more or less, moves across the sky to the west, and then sets. Right. And if you take a vertical object like the little homemade sundial I have in the video clip at the bottom, it casts a shadow that sweeps across in the opposite direction. Right. The shadow points in a sort of westerly direction as the sun rises, and then in an easterly direction later in the day. If you keep track of the position of that shadow, you can tell where you are in the course of the day. You can tell what time it is based on where the sun is in the sky. And so some of the oldest timekeepers that we have are sundials, which are essentially clocks that in some sense tick once a day, right? As the sun moves from one side of the sky to the other, the shadow sweeps along, and you can tell where you are by using that repeating pattern. Now, we can also make clocks that are based on the motion of the sun over longer time scales. Now, the sun doesn't just move east and west, it also moves north and south. This is something that people at our latitude are acutely aware of, particularly now when it's freezing cold and it's dark at 4 in the afternoon. The sun moves north and south as the Earth moves around it in its orbit, and the tilt of the axis changes. And so if you take a picture of the sun at the same time every day, for a year, it traces out this sort of figure-8 shaped pattern in the sky. It's called an analemma. And that reflects the fact that the rising and setting position of the sun is moving along the horizon. So in the summer, the sun rises to the north of east and it sets to the north of west. And in the winter, it rises well to the south of east and sets well to the south of west. This means that the position where the sun rises or sets on the horizon can also serve as a kind of clock, one that moves incredibly slowly, that ticks just once a year. And that's the other thing that I had in that first slide. This New Grange Monument outside of Dublin in Ireland. This is a passage tomb from Neolithic times. And this consists of a giant artificial hill of rocks and dirt piled up, about 100,000 metric tons. And there's a chamber in the center of this that's reached by a long, narrow passageway that goes into the center of the mound. And this passageway is aligned so that on the winter solstice, on the solstice in December, the shortest day of the year, the rising sun casts a ray through a slit over the door to this that leads into this passage. That ray goes all the way down the passageway into the central chamber, and it's the only time all year that central chamber gets lit up. So this is a dramatic indicator that you've reached the winter solstice, that the sun is rising at the southernmost point on the horizon that it's going to. And that's really critical information if you're doing, if you're in an agrarian society, right? You need to know, okay, now we've reached the point where the days have gotten as short as they're going to get, things are going to get better from here. And now we need to start thinking about, okay, preparing for spring, which is coming, and, harvesting plants and animals and all of those kinds of things. So this is incredibly important, so important that people put enormous effort into, dragging these massive stones around and building this gigantic hill in 3200 BCE. So this thing is over 5,000 years old, and it still works as a clock today. You can actually, if you go to visit the monument, you can put your name into a lottery to be in the central chamber on December 21st, when the rising sun is going to cast that ray of light down. And so you can see this and experience it firsthand. Though, since it's located in Ireland, they are very careful to note that there are no refunds in the event that it's cloudy and the sun doesn't actually come up. So these are examples of really ancient clocks that are based on the motion of the sun. But even, also almost as ancient are technologies for keeping time when the sun's not visible, right? So when it's cloudy, as it often is in Ireland and Schenectady and also New Hampshire, right? You need some way to know what time it is when you can't see the sun. And there are also extremely ancient ways of doing this. This is a thing called the Carnac clepsydra, which is a water clock. It is a alabaster vessel. It's shaped kind of like a flower pot, and it has a hole near the bottom that you fill this with water, and then the water slowly drains out. Right. That is another tick that you can use to mark the passage of time, which is done by having these fill marks on the inside of the chamber that you see in the drawing, reproduced in the drawing at the right. There's columns of numbers that show the different times for different levels of water. So you fill this up to the top, you let it drain out, and then by looking at what the water level is, you can say what time it is. And this is very regular and very repeatable. This particular water clock is built in dates from about 1300 BCE. And we actually have a name of someone who at least claims to have invented this, which was a couple hundred years earlier, around 1500 BC. There's a fellow who was a court official in Egypt named Amenemhet, whose tomb inscription includes a claim that he had invented a remarkable water clock that could keep accurate time through the course of the night, and even at different times of year. What is that? Well, that's probably this device that we're looking at in this photo, because you can see there's 12 columns of numbers. These correspond to the different months of the year, and the spacing of the time marks is different in the different months. In the winter months, the marks are closer together, reflecting the fact that the nights, in the summer months, the marks are closer together, reflecting the fact that the nights are relatively short. And in the winter months, they're farther apart, the nights are longer, so you allow more time to drain. There's also a really clever feature of this in that the fact that this is tapered makes the rate at which the water drains much more regular. And so this is actually a very clever bit of engineering that was done, 3,000 years ago. So people have been working hard to make precision timekeepers for thousands and thousands of years. Now, this basic idea of a water clock, of something that you fill up and you let water drain out, or in some other variations, you make a source that provides water at a constant rate, and then you look at how long it takes to fill some container. Same idea either way. Clocks based on the flow of water were the state of the art in timekeeping all the way up into the Renaissance, when mechanical clocks are finally introduced. And they're really only surpassed in precision in 1657, when the pendulum clock is invented. The first pendulum clock gets built. And these mark time by, a massive object swinging back and forth, like the pendulum in a grandfather clock. Or in this little video clip here, this is the pendulum inside the chapel clock. This is Union College's Memorial Chapel, Union College, where I teach. This is the works of that clock. And you can see this is what introduces the tick-tock sound that we associate with timekeeping, and that I use as a metaphor when I talk about a clock being a thing that ticks, right? There are gear faces that are dipping in and out of the gear, stopping its motion and causing this to move at a very regular rate. The swinging of a pendulum, it turns out, is incredibly regular. And it makes an ideal basis for a mechanical clock. They work incredibly well, and these supplanted water clocks very quickly. You can make pendulum clocks that are good to a few minutes a year, right? And that's really remarkably good. That revolutionizes a lot of astronomy, and everybody starts using these. These are the standard up into the 20th century. So there's thousands and thousands of years of this. Pendulum clocks take over. They have a very good run from the 1600s up into the 1900s. And they get replaced by another physical moving thing, which is what powers basically any watch you can buy for a reasonable amount of money these days. And that's this what we see on the left here is a little sort of tuning fork made out of quartz crystal. Right, so you can see that clear material is quartz glass, and that vibrates very rapidly. It's a very stiff material, so it vibrates at a high frequency, and it has electrical properties that mean you can start it vibrating by applying a little bit of a voltage, and you can also measure the vibration using a little bit of a voltage. So this is a perfect device for timekeeping in a compact electronic form. So these are developed in the around 1930 as the first quartz timekeepers get made, and these are phenomenally better than mechanical clocks based on pendulums. The initial ones are very clunky and expensive, but by the 1960s, the quartz clocks blow everything else away. There's nothing better in the timekeeping world, and by the 1970s, they're cheap too. So nowadays, any clock that you find, a watch, unless it's a really high-end mechanical watch, any watch that you have will have one of these little quartz oscillators in it to keep time. Again, by looking at the regular repeated action of this little tuning fork vibrating back and forth. Now, the ultimate standard of time that we use today is actually something even smaller than these tiny little tuning forks that fit inside the watch. It's atoms, specifically atoms of cesium. We define time now as 1 second is defined as 9,192,631,770 oscillations of the light absorbed or emitted as cesium atoms move between two energy states. So these are clocks now that are really have no moving parts, right? They're using the oscillation of light. They're counting those oscillations to determine how much time has passed. That's the tick, and it's an incredibly fast tick. And the way that you determine the frequency, the way that you know you have the right light, is by exposing it to cesium atoms and using these cesium atoms as perfect little references for this particular frequency of light. So we know that the energy difference in cesium atoms is determined by fundamental laws of physics. That means that every cesium-133 atom in the universe is identical to every other cesium-133 atom in the universe. So they're all potentially perfect references for a clock. And we now build atomic clocks that are based on producing this microwave frequency and measuring it to incredibly high precision. These are now clocks that are good to, you could run one of these continuously for something like 1 billion years before it would build up enough error to add up to a single second. So there's this thousands of years long process of evolution in timekeeping that is a process of identifying and refining different kinds of ticks that you can count, different kinds of regular repeated actions that you can count and use to measure the passage of time. So we start with the motion of the sun, both along the horizon as the seasons change and across the sky as days go by. We move to the ticks of a water clock, of a regular flow of water, either in or out of a container. And then the tick that we mostly think of, which is something like a pendulum swinging back and forth, a mechanical object. And those clocks can be good to, seconds a day, that kind of level of precision. Then you get to quartz oscillators that can be good to, seconds a month if you have a really high quality one. And then onto these cesium clocks that are good to, that are looking at the oscillations of light waves, and those are good to, a second in 1 billion years. Right. Now, a question you could ask is, why are we trying to measure time to this level of precision? Why does anybody need a clock that's good to a second in 1 billion years? Because nobody's going to be around when it finally ends up being 1 second off. Right. The answer to that has to do with navigation, and that's another big theme that runs through the book, is looking at differences in place. Right. If you look at a map of the world, right, you can talk about longitude, but there are also these time zones, right, that go across the world. It's different times in different places. I saw in the chat some people are joining us from the Midwest. I saw somebody, I think, in Minnesota. Right, the time there is an hour different than the time where I'm sitting in Schenectady, New York. And that reflects the fact that the Earth is a rotating sphere, and time as measured by the sun is going to be different for people in different places, because you're going to see the sun in a different position depending on where you are on the Earth. We account for this by setting up this system of time zones that spans the Earth, right? And then what time it is where you are depends on your longitude, right? You can also turn this around and say that if you know the time, you know the time in 2 different places, that will tell you the difference in longitude between those 2 places. And this becomes incredibly important as the European empires start to expand to cover the entire globe, right? As people are sailing from Europe to the Americas and to Asia, right, then they're now covering huge distances of open ocean, and you need to know where you are in that ocean. You need to know the time. And so this is a very big problem that people have to solve. There are 2 problems with this historically in the 1700s. There's 2 approaches to solving this problem, rather. One approach is just to build an incredibly good clock that can keep track of the time well enough that you know where you are, and you know the time where you are by looking at the sun. You know what time it is in London by looking at your watch, and that difference tells you your longitude. And this is finally accomplished by this fellow here, the clockmaker John Harrison in the 1760s, comes up with the watch on the right. Is finally the first timekeeper that's truly good enough to keep time at sea well enough to measure longitude. The other approach to this involves astronomy, right? Another way to know the difference in time between two places is to look at something that you can see from both places, right? And if you know where it appears to be where you are and where it should be someplace else, right? What time it should be in that position seen from someplace else, that tells you the difference in time. A really good object to use for this is the moon, right? So we're all familiar with the moon, which has phases, right? You go outside at night, you know, I have to, we have a dog. I have to walk the dog in the evening. I get to see the change of the moon all the time, right? As the moon goes around the earth, it is lit. We see different portions of the lit surface, and that gets us this, you know, this pattern of phases that's very familiar. The moon also moves relative to the background of the stars, right? So it moves about 13 degrees per day, which means over the course of a few hours, it moves by its own diameter, you know, several of its own diameters, which is enough to allow you to keep track of the time well enough to measure longitude. Now, this is a really hard problem in astronomy, and it takes a lot of work, much of which is done by this fellow here, Tobias Meyer, who does the hard work of calculating all of the parameters of the moon's orbit around the Earth, and then the Earth's orbit around the sun, and how those things interact with each other. Does those calculations to be able to predict where the moon will be relative to the stars at specific times for years into the future. And this is turned into a set of navigational tables by this fellow here, the Astronomer Royal Neville Maskelyne, who generates these nautical almanacs that sailors can use starting in the 1760s to measure what they call lunar distances, right? You measure the separation in the sky between the moon and some bright star, and that tells you, right, you can look at where the moon is predicted to be, and that tells you the time. Excuse me. So these two solutions are developed right around the same time in the 1760s to the problem of navigation at sea, finding time either by a watch or by this method of lunar distances. These are chronicled in great detail in two other books that I'll mention here. The book Longitude by David Sobel is extremely famous, you know, bestseller, won some awards. This tells primarily the story of Harrison and the development of his clocks. There's also, this is a less well-known book, but this is associated with a very good exhibit at the Royal Museum in Greenwich that looked at this longitude problem in much more detail, and is a more complete version of the story. So ships, clocks, and stars. Now you might be saying, well, okay, that's great if you're in 1700 and want to navigate, but you know, that's what you need there is clocks that are good to, you know, a second a day on shipboard, and that's impressive engineering, but that's not like an atomic clock that's good to a second in a billion years. Why do we need those? The answer is still navigation, and in modern times that's done through the global positioning system. So if you have a navigation app on your phone, or you play one of those little augmented reality games, right, you are using your smartphone to measure your position on the Earth through the global positioning system, which is a network of satellites that contain clocks, and they broadcast a coded signal that says what satellite the signal is coming from and what time it is according to the clock on that satellite. Now, how does that help you? Well, we know that those signals from the satellites are traveling to the receiver at the speed of light, carried by radio waves. And that means that if you get the time signals from several different satellites, they'll differ by a little bit because the satellites are different distances away from your position. You can turn those time differences into distances to the satellite. You can work backwards and say, okay, I'm this far from that one, and that this far from that one, and this far from that other one. And that allows you to find your position on the face of the earth. That might seem weird, but it's not that different than something that we do quite regularly, which is, right, I live in Schenectady, New York, which is not a super famous city. Not a lot of people know where that is, but I can tell people roughly where it is by saying, well, we're 3 hours from Boston. All right, 3 hours from Boston puts us somewhere on this green circle on a map of New England, right, which is, you know, roughly 180 miles radius around Boston. So, you know, that includes Schenectady, but that also includes a lot of northern New Hampshire and then central Vermont and, you know, some stuff in Connecticut. So that's not all that informative. But I can also tell people that, you know, in addition to being 3 hours drive from Boston, we're 3 hours drive from New York, right? And that puts us somewhere on a circle of the same radius, centered on New York City. And there's only 2 places on the earth where those 2 circles cross each other. One of them is Schenectady, the other is in the North Atlantic. So, you know, you can probably figure out from that which one is the place where I live. But if you really want to be precise about it, I can also say we're 4 hours drive from Montreal, and there's only one place on the surface of the earth where all 3 of those circles intersect. This is the same process that you're doing with the satellites in the GPS constellation. You're saying, okay, you know, I'm this many milliseconds away from that satellite and that many milliseconds away from this other satellite, and using those to determine distances that put you at a single point on the surface of the earth. Now, these satellites involve atomic clocks to do this because light travels at an extremely high speed. Light travels at a speed of about 1 foot per nanosecond, right? So you need nanosecond timing to be able to use these time signals from satellites to get your position accurately enough to be useful. So these satellites all contain atomic clocks based on cesium atoms that are producing these time signals and sending those signals out to be received to allow you to locate yourself on the surface of the earth. And this is why scientists work so hard at making these ultra precise atomic clocks, because this ultimately feeds into the intensely practical issue of how you navigate. So that gives you sort of a survey of some of the areas of science that we talk about in the book. I also want to mention that, you know, this is a very human story as well, and so has a lot of other aspects to it. In particular, there are aspects of politics to the story that are kind of interesting. So this is a map of the time zones in the U.S. showing this patchwork of local times that we operated on prior to the introduction of standardized time in the 1880s. And you can see that, you know, if you look closely, you see that, you know, say New York City, when it was, you know, it was 12:12 in New York City. It was, you know, 12:07 in Philadelphia, and, you know, 12:03 down in Southern Virginia, and so on, right? Every city had its own time. And the process by which we introduced the standardization of time to say that you know, people in Eastern Maine and Western Ohio are going to set their clocks to the same hour is a very fascinating and political process. And we talk about that a bit in the book. This was originally done by the railroads. And, you know, even farther back in history, there are things like the introduction of the Gregorian calendar that we use now in the West. This happens in the 1580s and is done again by a complicated process of bringing together a bunch of astronomical experts, but also theologians to figure out, you know, what is exactly the right way to set up a calendar that will meet the religious needs of the Catholic Church and introduce that. So again, a very interesting, very human sort of process that goes on. And this also covers, you know, timekeeping is a thing that is universal. I talk in the book about a lot of systems in Europe and the Mediterranean area, but also some really fantastic clocks that are built in China in the medieval period. And there's also a whole bit about the Mayan calendar. So this is a few pages from one of the few surviving books that were made by the Maya in Central America that survived the Spanish conquest. And this is these pages show tables of numbers that are predictions for the rising and setting times of the planet Venus. The Maya were in fact really accomplished astronomers and did a very good job of this problem that I talked about earlier in the context of navigation, of being able to predict where will things that we see moving around the sky, where will they be in the future, right? And the Maya had these highly developed tables that could predict the rising and setting times of Venus for a span of several centuries. So really good and really interesting. And they had a remarkably rich and complicated culture associated with this timekeeping as well. That's really fascinating, and I talk about that in the book as well. So that's a bit about what the book is about, to give you some flavor of what it is and the depth and richness of the history of timekeeping that I'm talking about here. And I will stop there, and I will be happy to answer any questions that have come up as I've been talking about them.
All right, I'm gonna stop your share here. We do have a couple questions popping in. A couple of them I didn't quite get the context of. So I'm gonna ask Sean, you said, what about special and general relativity? I don't remember when you mentioned that, but Chad, you're nodding all of a sudden. So
yeah, so special and general relativity, these are Einstein's theories that famously relate space and time to each other, and this tells you that if you have two clocks that are identical and you're holding one with you and watching one move by, you will see the moving clock running slow, right? And in reverse, if some other person is moving with that other clock, they'll see your clock running slow, right? So every observer will see everybody else's clocks running at different rates. Now, this, on a philosophical level, this is really interesting, because it means that time, in a deep sense, truly is a personal thing, right? That everybody's perception of time is going to be slightly different because of how they've been moving, right? General relativity is an extension of special relativity that incorporates gravity. And that tells you that time, the rate at which clocks tick, changes based on where you are relative to a massive object. So a clock that's at a low altitude, close to the Earth, ticks slightly slower than one that's higher up. And these are both verified in experiments with ultra precise atomic clocks. These have real implications for GPS. So the global positioning system is satellites containing atomic clocks. Those satellites are moving very fast because they're orbiting the Earth. They're also very high up, so they tick a little bit slow compared to identical clocks on the ground because they're in orbit and moving rapidly. And they tick a little bit fast because they're very high up. The combination of the two means that if you just made the clocks perfectly identical and put, a clock from the ground into the satellite and shot it up there and put it in orbit, the clock would be slow would run fast by about 34 microseconds a day, right? And so this is would be a problem for the navigation system, but the scientists and engineers who built the system know about Einstein's relativity, and they built in a correction. So those clocks are designed so that they run at a slightly different rate by design that exactly compensates for that difference. So they keep perfect time, even though they're in orbit, moving very fast and very high up.
This is fascinating. And I love that you knew off the top of your head that it was 34 microseconds a day.
I do this a bunch.
I adore this. This is fantastic.
Of course, I could also be getting that wrong and nobody would know.
Well, that's true. Now that you mention it, I just believed you.
So actually, where you are, there's probably it would not surprise me if somebody in your audience knows exactly what the number is, because there's a lot of very smart people in your part of New Hampshire.
You know what? It's true. And if anybody who's watching this later on YouTube, or anybody in our audience right now wants to correct Chad, just leave a comment. That'd be great. Carolyn wants to know, what kind of measurement was used with smaller timepieces before the 1900s, such as pocket watches?
So what you do for a pocket watch is it's a similar idea to using a pendulum to make a clock. But instead of, if you're going to have a watch, right, the orientation of it is going to be changing all the time. So what you need to do is something that doesn't depend on being vertical. And for that, you use it's called a balance wheel, which is like a little ring of metal that's attached to a spring. And so it twists back and forth. And that twisting back and forth, it turns out, depends almost entirely on the properties of the spring. So if you manufacture the springs properly, they can be extremely reliable. And that's what a lot of what John Harrison's development of the watch for navigation, a lot of the key to that was the getting that just right, figuring out exactly what are the best materials to make the spring from, how do you keep the gears from seizing up, and all that kind of thing.
To make that a little bit literary, is that why in older books, gentlemen were winding their pocket watches?
Yeah, so you also power it with a spring. So you have a coiled spring that's putting tension on the gear. It's trying to make the gears spin. And then you have this little spring that's going back and forth, that's as it twists back and forth, it lets the gear move by just a little bit. So you're winding that spring up. We have a pendulum clock that we keep in our dining room that has to be wound almost daily. And it's the same thing. There's a spring that's trying to drive the gears, and then the pendulum swinging back and forth at different points stops the gears so that it turns only 1 tooth per second.
So we have a question from fairly early in our event when you were still discussing water clocks. How accurate were those? I mean, it's probably hard to answer that, but
they could be quite good. You can make a water clock that the flow is very constant. Galileo Galilei actually did a number of experiments on pendulums. He's one of the first to study the pendulum in great detail, and a lot of his measurements were made using a water clock. He had a sort of constant flow water source, and he would time things by, when he started it, he'd take his thumb off the outlet, and then when it got to whatever point he was trying to measure, he'd plug it up again, and then he'd weigh the water that had collected in a little container. And so these were really accurate at timing these short intervals. If you wanted to make a water clock that runs for a long time, it's a little more challenging. But there's a very famous one built in China around 1100. It's the Tower Clock of Susong. I talk about it in the book. That was this marvelous, ginormous clock that had, a huge wheel that was driven by the water. It turned at a constant rate and drove all of this, automata and celestial globe and all these other things to keep time. And it was very good. So it was, not seconds per year, but minutes. So quite accurate.
So I have a question, and that is, as someone who often struggles with timeliness, societies all around the world seem to have developed methods of timekeeping. Why is what I want to know. I mean, it makes sense that you'd want to know roughly, okay, we're this way through the winter, and the winter will not last forever, and we can anticipate for the future. But now we have oh, you're 45 seconds late, and it's stressful. Why are we doing this to ourselves?
Well, the issue is, the original issue is really agriculture, right? You need to know, what time of year you should be planting crops and all that kind of thing. But there's also sort of a coordination issue, right? As societies start to get bigger, right, you need to have larger numbers of people who don't all live together, able to coordinate their actions, right? So you want to be able to say, okay, like we need to, you and I need to get together and talk about this book that we're going to sell, right? We need to do that at a particular, we need to be in the same place at the same time to do that. So timekeeping gives you a way to start to coordinate that. And so you see, timekeeping, as cities start to get big, there starts to be sort of public timekeeping, right? There in Rome and China, they have, drums and trumpets and things that they sound on the hours so that everybody knows what time it is. And then that gives you a way to say, okay, now now it's the 3rd hour afternoon. I'm supposed to be meeting Elizabeth at, this restaurant at this time. And so you have this coordination thing as societies get more complicated.
All right, that makes a lot more sense. I was presuming that our ancestors specifically were targeting me, but I guess that makes sense. So I'll allow it. Janine wants to know, 1, is it possible to have an atomic clock repaired, and at what cost? And 2, what does the shirt say on the chair behind you?
So in reverse order, the shirt on the chair behind me says "Not Today COVID," and it's not with 2 T's. And the reason for that is there's a building on the Union College campus that is the Knott Memorial, named after one of our early presidents. And it's the signature building for the college. It's on the letterhead and all that kind of thing. And these were handed out when we set up vaccination clinics for students. So as we were doing giving out the vaccines, they made these shirts and handed them out, and they were enormously popular. And so I have that there as a tribute to that. The other question about atomic clock repair, you can buy commercial atomic clocks. They're very expensive, tens of thousands of dollars. And I presume that if it breaks, you can get Hewlett Packard to repair it. But I don't know. Most of the people who use these are in a context of standards laboratories. So, they have, I have a friend who works at the US Naval Observatory. You can go down there. They've got, a dozen atomic clocks, in equipment racks all lined up next to each other. And they're using a complicated combination of the times from all of these clocks. They're constantly evaluating the performance of each clock. And so they do all their own repairs in-house, right? So whatever, if something breaks, then they just fix it there, because that's their business.
All right. Elaine wants to know, what was the most surprising thing you learned while writing this book, which sort of ties into someone asking earlier in the chat, the favorite question, where do you get your ideas from? And someone had the joke of from a phone booth in Schenectady.
Oh, right. That's a famous flippant response from a famous author, Harlan Ellison. Would tell people, like, yeah, I get my ideas I send $5 a month to a little old lady in Schenectady who sends me back, 10 good ideas. Which
is presumably where you got the idea for this book. So what?
The origin of this book actually originates partly as a course that I've taught here with this title, Brief History of Timekeeping. Because it has this, this incredibly deep and rich history, and it crosses a bunch of cultures. We're a liberal arts college, so this is a course that we offer to. I had arts students and engineering majors in the same course, teaching all of them something about this. So it was a great format for that. The most surprising thing that I learned while researching, actually initially the course, but it's in the book. The thing that was the biggest surprise is if you have an hourglass. I used to have one on my desk here, but I don't know what I did with it. A little sand timer right? An hourglass. You would think that that's an incredibly ancient technology, but it's actually invented right around the same time as mechanical clocks. The first unambiguous depiction we have of an hourglass, of a sand timer, is from the early 1300s in a painting in Siena, Italy. And the first mechanical clocks were invented in sometime in the 1200s. We're really hazy on both of those things. There isn't a clear invention date for the very first mechanical clock, which was not a pendulum clock. We know when the first pendulum clock was and who made that. But the very first mechanical clocks and just sort of show up. And the sand timers were presumably in use for a good while before 1330 when they show up in this painting, because, you know, people looking at the painting had to know what it was. So, you know, it had to be obvious to them what that thing was. So, you know, probably they're both invented sometime in the 1200s, but they used to use the same word sort of indiscriminately for all kinds of timekeepers in record keeping. So you have to sort of work backwards and figure out what kind of clock it was from other clues in the context. So like there's a monastery in England that they had a fire, and there's a record in the chronicles of this monastery. They say, you know, the fire broke out and some of the brothers ran to the well and some of the brothers ran to the clock. Well, the reason they ran to the clock is because it's a water clock, and so they're going there to fill buckets of water to throw on the fire. There's other mentions of, you know, a clock was installed in a really high place in a church. That's probably not a water clock. That's probably an early mechanical clock, because nobody wants to go, you know, haul buckets of water up, you know, 50 flights of stairs. So, and sand glasses are presumably showing up in there, but just nobody really knows. It's hard to figure out.
Also, you have to have the invention of glass blowing. Or
yeah, the big issue is it's the glass and the sand. And for hundreds of years, it was like a big business to, you know, find the best stuff to put in your sand timer. And so, you know, people had secret recipes for this and arguments about it, and these kinds of things. And the key is getting the glass blowing and the materials so that the sand doesn't clump up and it flows at a regular rate. Those are also remarkably good. I have, like I said, I used to have one sitting right here, but I don't know what I did with it. But I bought a box of cheap, you know, sand timers, you know, get 20 of them for $3 from Amazon, and had students measure them, you know, like how long does it take to empty this way and then this way, and just repeat that over and over. They're remarkably repeatable. They're, you know, and these are made with modern glass blowing technology and materials and all that kind of thing. But, you know, it's like good to within, you know, it was like they were like a 3-minute timer, and they were good to within a couple of seconds. So so really, like, you wouldn't think it would be that repeatable, but it's really very good.
All right. So Colin wants to know, was your dog not interested in timekeeping, as your previous dogs were about teaching science to your dog?
The dog is actually here. I'll turn my camera off briefly, and there's a picture of our current dog. This is Charlie the pupper, who's a very good boy. The dog is in fact intensely interested in timekeeping, in that, you know, he wants to be sure that he gets fed at the appropriate time, which, as far as he's concerned, is the earliest hour that he has ever been fed dinner. So yeah, that's when he starts looking for it.
They say if you want to remember a daily task, what one should do is feed your cat or dog a treat at the same time, because they will not let you.
Right. They'll come get you and remind you. Yes.
Matthew wants to know, why would a mountainous and landlocked country like Switzerland be world famous in regards to clocks?
It's a really interesting thing that happens in like the 1800s. The Swiss started manufacturing timepieces as an industry. It's something that you could do in sort of communities where it's not great for farming, and like you're up in the mountains and it's, you know, they have long winters and that kind of thing. And they would do it as sort of piecework. People figured out the idea of, okay, you know, we're going to have, you know, this family is just going to make gears and this family is going to do springs, right? And they would sort of, you know, there would be like something like, you know, 20 or 30 people involved in making the parts to assemble a single watch. But they standardized this and distributed it, and it became a huge cash enterprise for them. It actually drifted in from some nearby regions in France, is where the clockmaking started. But the Swiss took it up with you know, great enthusiasm and developed this process that started making these really exceptional timepieces in the 1800s.
Sean wants to know, do the pros and cons of daylight savings time make it useless now?
So the thing with daylight savings time is every time the time change comes around, there's, you know, people are like, why don't we just stay on daylight time all year round? And the answer is December, because if you stayed on daylight time all year round, at our latitude, like Schenectady and Concord are not that far different. At our latitude, the sun in mid-December would not rise until 8:30 in the morning. And it's dark and depressing and everybody would hate it. So the advantage of going back to standard time for the winter months is that now the sun's rising at a more reasonable hour. I mean, it's still rising after my kids are getting on the school bus, but it's at a more reasonable hour. The advantage of daylight saving time is you have those lovely long summer evenings, right? So there's a lot of time after dinner when it's still light out. You can have baseball games outdoors and picnics and all of the things that we love doing in the summer. So psychologically, the advantages of the switch are very clear, right? You get more reasonable light in the morning in the winter and those long summer evenings. The problem with daylight savings is that you have those two time changes, right? And it's actually really only one of them that's the problem. It's like the one in the fall is not so bad because, you know, you fall back, but, you know, it's confusing. You have to reset all the clocks, but you get an extra hour of sleep, right? Which is fantastic. So that one is not bad. It's the spring one where you go forward an hour and you lose an hour of sleep and everybody's cranky and discombobulated for a week, right? That's bad. So my modest proposal, which is one of many things that will keep me from ever holding elective office. My proposal is we should keep the fall back in November, but rather than doing a spring forward in March, starting on the December solstice, December 21st, every Saturday after that for 12 weeks, we should move the clocks forward 5 minutes, right? And so that's a small enough, you lose 5 minutes of sleep in a week, nobody's going to even notice that, right? And then over the course of about 3 months, by, you know, mid-March, we're back to daylight saving time. And then you've got the long summer evenings without the trauma of spring forward and everybody losing an hour of sleep. So that's my proposal for how to reform daylight savings time. Now, you know, everybody says that's way too complicated. You have to reset all these clocks. But, you know, most people nowadays are, you know, you're getting your time off something that's internet connected, right? You're getting your time off a phone that just updates automatically, right? So it's not that big a deal. So.
Well, actually, somebody has a question here in chat. They say they have an atomic clock. They have a clock that sets itself automatically by the atomic clock, and it's off by 8 minutes. How do they go about finding an atomic clock to fix it?
That I don't know. You can get these clocks that are they sync to used to be a radio signal that was put out by, I forget if it must be NIST, must be the National Institute of Standards and Technology, for civilian purposes. There's like a radio signal that they send out to synchronize clocks, so you can get these atomic clocks that are really just synchronizing themselves to the atomic time broadcast. You can also get them these days that they get the time from the GPS network. How it would be off by 8 minutes, I have no idea. That's
it is a very specific amount of time to be off.
Yeah, that's we used to have, the old building that my office used to be in. I had a clock outside my office that was just permanently stopped at 8:55. So it always looked like it was, 5 minutes to 9, which was I always thought was ironic for a science building that the clock didn't work. But it was sort of a nice metaphysical commentary that I was always 5 minutes away from starting work. So.
Let's see. I think we had one more question here to answer. Yeah, someone said, I think Elaine, my dog is a great clock. Time to go out, time to eat, time to take a clock, time to go to bed. I like this kind of timekeeping. I'm a neurodivergent in that I have a little bit of time blindness. So it's frustration, like I don't really process the passage of time in my head and oops, it's time to go. So I would like that.
Yes.
It's time to eat, it's time to do the thing. Let's see. Carolyn says, I was surprised to learn how rare clocks were in the US in homes not too long ago. Do you have more information about when and how this changed?
So it was, clocks were big, expensive items up through much of the 1800s, right? Because they're hard to make, right? It's a precision device that's difficult to manufacture in really large quantities. So like, grandfather clocks, like the reason they're heirlooms and antiques is that, if you got one, you kept it around for a long time because somebody spent a lot of money on this, right? That really starts to change in the late 1800s, where you get the rise of what were called dollar watches. So they got the price of a single wristwatch down to $1, and that was about, it's not a trivial amount of money, but that was about 1 day's wages for a manual laborer, and then that really democratizes time in a big way, and so people, kind of everybody starts to be able to have a watch that could keep reasonably accurate time. Now, those aren't fantastic timekeepers relative to, your really expensive pendulum clocks and that sort of thing. But they're good enough. And, in that same time period, we're standardizing time, and, you have big public clocks in railway stations and department stores and all over the place that you can use to reset your watch. So if you have to reset your watch every couple of days because it loses a minute over the course of a week, it's no big deal, right? And that sort of public dissemination of time, continues all over the place. I grew up in a very rural area in New York State. We had the noon whistle, right? Every day at exactly 12 o'clock at noon, they would sound the siren and for the volunteer fire department, because people working in farm fields, then you could hear that, okay, now it's noon, and if you had a watch, you could set it accordingly, and then know that your time was right for the rest of the day, right? That sort of thing was extremely common for allowing people to have an idea of what time it was, without having big expensive clocks in their home.
All right. So one last question before I ask our last question of the night. I do want to say thank you very much for joining us tonight.
Thank you for having me. This has been fun.
This has been a lot of fun. This has been fascinating. I love the minutia of history. I love when someone goes in a deep dive and says, here are the societal implications of like a fork or a clock or like a belt. It's just, I love it. And I would like to remind our audience members that we do have this book here in the store. We are happy to ship it to you, curbside pickup, in-store browsing, A Brief History of Timekeeping, the Science of Marking Time from Stonehenge to Atomic Clocks. Please do put in an order. Congratulations on your publication. It's only about a week old, I think, a week.
It came out Tuesday, actually.
Tuesday.
So 2 days old. So.
2 days old. Congratulations. Our last question is, do you have a favorite clock, a favorite wristwatch, a favorite?
The watch that I've got on here, this isn't anything super special. This is it's a Seiko quartz watch. You know, I think I've had to replace the band. I've had it long enough that I've had to replace the band enough times that I probably spent more on bands than I spent on the watch. I do have an heirloom mechanical watch from the 60s that we inherited from a dear friend of the family that is an Omega watch from that's really cool. It's a purely mechanical watch from the 60s. That's really cool. The historical clock that I think I was most impressed by, that I like reading about in the course of researching the book, is that tower clock in China, which is just a fascinating. It's an incredible piece of engineering that they devised in around 1100. That it has this really intricate mechanism of converting this constant flow water source into the driving power and the regulation for this wheel, and turning all this the displays and stuff that it did. So that was the coolest of the ones that I've researched.
And they can read about it in your book.
Yes.
Which is A Brief History of Timekeeping. Thank you very, very much for joining us this evening. To our audience members, thank you for joining us as well. I hope everybody has a great night. Looks like we're out of time.
Yep. So
have a great night, everybody.
Thank you.